Hi all, welcome back. So I'm coming back to solve one more question asked in the electrical gate exam and this year, gate 2025. So all right, those this series is going to helpful for those who are preparing for gate exam or those who want to understand the concepts through questions. All right. So let us read out the question they ask. So they given the one transfer function gs equal to 1 by s plus 1 into s plus 2 they given, and the closed loop system we need to find out, and what's the they want to hear, they want that for what is a k range system is stable unstable, like that we need to find out. So for those how we can solve out, we can solve it this question through apply the Routh-Hurwitz criterion. Okay, Routh-Hurwitz criterion in this we can find out what is the maximum uh, k value. Okay, yeah, what's the range where system is stable or unstable, like that we can find out. Okay, so before to solve this question, let me go through the some concept overview of the Routh-Hurwitz. Okay, so I think it is easy to recall and solve this question. Okay, so here, like in Routh-Hurwitz criterion, determine the number of routes. Basically, Routh-Hurwitz criterion we have to utilize, we have to use for find out the number of routes where is a lie in the left of the S plane. Okay, in general sense we can say we can find out the routes. Okay, so where is basically there is a left hand side, right hand side. Okay, so these things rather than find out the exact number, we can find a number of routes. Okay, my point is that here like this your S plane. Okay, so this is j omega axis and this our real axis. Okay, and this my left of the S plane, this my right of the S plane, right of the S plane. Okay, and this is my j omega axis, you can see. So here we can find out the number of routes where is a like right of the plane or left of the plane, or remaining is a j omega axis. So that's why we can find out if a number of poles right of the plane, so we can system unstable. So okay, so first and fundamental, we have to check all coefficients should be in same sign. Okay, if same sign not there, straight away we can system unstable. But how many number of poles right hand side, this thing we need to see, we need to solve, we need to develop the route table. Okay, and then we see the first column of the route table and then see check the number of changes in signs. Okay, we'll see how we can say construct the tabular form route array and examine the sign change in the first column. That's a very important here, we need to understand this. Number of sign change in first column shows that number of the equal to number of poles in right hand of the S plane. This shows that system unstable. And how many number of poles in right hand of the S plane? This shows the number of sign changes. All right. So how we can consider it? Routh-Hurwitz pattern. You can see first we have to our characterization, but our polynomial we want to find out the roots, so we have to put just arrange as a descending order and take a higher order first, and then just for lower order degree, you can say. Okay, so and then put the coefficient like that. Okay, sorry, this side enter and then like that. Okay, compute the subsequent row like a b c d. How we can find out, we can say find out like b1, you can say this is b1. Okay, so a1 multiply a2 minus a0 into a3 divided by a1, like that we can find out. And just we have to extend this like this one, a1 into a4 minus a naught into a5 by divided by a1, and so on. We can continue until we reach the constant value s power 0. Okay, so if some coefficient like is not is something missing, so that time we can say we put the 0. If something missing, that time also it clearly tells that system one, at least one pole would lie on the right of the S-plane. Okay, so in control system, route theory generally we have to use in a find out the, rather than finding the exact location of pole, if we know the okay, poles lie on the right hand of the S-plane. Yeah, at least if one pole lie on the right of the S-plane, it also signifies like our system is unstable, right? So, so that's why there's no need to explicit find out the pole's location. Straight away we can find out the, still we can find tells about the stability of the system. Okay, so in the work question they find out what's the k range our system is stable or yeah, unstable. Either of the case can possible. So whenever you develop this, create this tabular form, some special case also form. Okay, like if 0 as the first element of row, so that's also important here. Replace 0 with a small positive value called the epsilon. Okay, and proceed for calculation. But this one thing that if we found one 0 at in the row, okay, first element, this signifies that at least one pole at the right of the S-plane. But how many number of poles? So we need to complete the uh, column of the row service and then see number of sign changes. Okay, all right. And second row, second case, special case will be like entire row becomes 0. Okay, here only one element like first row, first element will be 0, remain is a non-zero. Okay, but here is a complete row 0. So what's the mean actually? Basically we get the symmetrical roots about the imaginary axis. What does that mean actually? Let us draw the possible case here. So like there are three cases we can say here, like this my real axis. I think some problem in writing pad. Okay, this is my j omega and this my sigma. Okay, so here our j omega is like a reflector, yeah, mirror we can say. Let us say one pole here and one pole here. Or second case we can say here, let us say this is like real pole. Okay, and let us say this is a complete imaginary pole, pure imaginary. Okay, this is marginal stable we can say. And one more case is also possible, complex pole, but complex will always lie in a conjugate nature, so that's why we have to form like that. Okay, so it's make like a square we can say. So point is that here in this both three cases, sorry, all three cases, we observe that we our poles as a symmetrical with respect to the our j omega axis. Okay, that time we observe we find the our a complete symmetrical complete row 0. Okay, so just below the complete 0 row, just above this row actually, we find one auxiliary polynomial. Just we have to solve it. If we get all poles as a imaginary pole, so all poles is imaginary. Okay, so we need to solve it. Okay, auxiliary polynomial. Just like this, like a 0, and just above it, we get polynomial, auxiliary polynomial. Okay, and just do the derivative and take a coefficient. We can complete our row service table, right? So I'm just giving here intuitive understanding here. Okay, because this question is not for related to this. Once we proceed to solve further questions, you will get this case and then be understand more better way. All right. So but point is that whenever we observe the symmetrical symmetry in roots, we get row is complete row is zero. But system is unstable, not stable, unstable. Okay, that's the we need to solve the auxiliary polynomial. If auxiliary polynomial is complete j mega imaginary imaginary poles roots, we can say, then we can say there is no the system is modular stable. Yeah, because this lie on the j omega axis. Okay, if like some pole is right hand side, then we can say it is unstable. Okay, so but once we have a understanding like symmetry will be there about the j omega axis, so only second case our pole will be not right hand of the s plane, but remaining two case, first and third case, our pole will be on the right of the s planes. This ensures that system is unstable. Okay, so I'm not going more deep in this, just you have to understand that why we about the region of this coming the complete row is zero. All right. Okay, so let us understand this all this stuff. So in the row theory, the first element they also called the pivot. Okay, of row becomes zero, but there are other non-zero element in the same row. So how we can basically find out? Okay, so division by zero in a computation of the next row is difficult. It leads to infinity. So that's why we just how we can resolve this issue and complete the our row service row. So make the array construction undefined at this point. So may indicate poles on imaginary axis, but not always. Okay, it may unstable also. Going to right hand axis. It's like a goose we can say. Only I think here you just understand that we can use that one pole, unstable pole will be there. Okay, how many number of pole will be there? We need to complete the our route service. All right. So that's the first case significance actually. So just they are giving like how we can handle this special case. So just put a small positive number and then we proceed for generally we symbolically present the epsilon. Okay, and then we put the just proceed for completion of route habit table and then put the we just solve the limit when epsilon leads to 0. All right, then we have to number of sign change in the first column indicates the number of unstable poles. Okay, so just like I just give an example like s square is equal to 0 4, you just put here epsilon here instead of 0 put the epsilon here. All right, so continue route area formation. Final result depends on the sign of the terms with epsilon when we put the epsilon tends to 0. Okay, so basically what's the main like points we can understand from this? Prevents failure in route array constructions, of course. If you come across this 0 at a first element, then we not go ahead to completion of the route service criterion table at least one first column. So we need to overcome, just put the positive number calling just epsilon. Okay, so we can complete it. So help handle marginal and near marginal stability cases. Okay, that's a very important point. Does not necessarily meaning imaginary roots use auxiliary test for that. So that's why I'm telling you like in case of our second case. So here we understood that we have to we have get a complete row 0, but in order to understand that all poles is similarly pole, so that time we need to solve the auxiliary equation polynomial. Okay, and then get it whether this is a complete imaginary axis imaginary roots or not. All right, so hope you understood and hope so maybe get a imaginary poles. In addition to this maybe get some poles right hand side, some pole left hand side, like that. Okay, because we have to maintain the symmetricity. All right, like for example, we can say like arithmetic polynomial is order 4. Okay, okay, so here order 4, so here is remaining, like for example, 2 pole is imaginary axis, and remaining 2 pole other than the, because symmetry will be maintained, so we need to put like that somewhere. Okay, so this like a club of the this first case and second case, so first and second possibility, right? So basically Rao therapy is very helpful in rather than find out the explicit number of poles, we still we can determine the stability and find out the range of variation of, how large we can increase the gain so that system to be stable. Okay, because when we design the control like proportional control or pi control, in this we need to ensure. Okay, so here so let us and understand the stability point of view. So stability condition and insights like complete stability means that the our first column of elements, our route table must be positive and non-zero. Okay, and marginal stable means the occur if there are no sign changes. Okay, but we found one row become zero. Okay, so this is a purely imaginary roots. Okay, na, that's why I'm telling you. Okay, if there no observation change, it means we but we observe the row become zero, so that's why we observe the all sign, all imaginary poles. All right, all right. So in stability, of course in stability at least one pole should be in a right of the plane. So if you find that the sign change in the first column equal to the right one right of the air pole. Okay, each sign changes, so one sign changes like plus to minus and plus. So this is a first sign changes and negative to plus. This is so two sign changes basically. So it means we two pole would lie on the right of the S plane. All right. Hope you understood. So ensure a not like some important things we need to understand, that observation in the route polynomial. So even in degree 0 row, so conjugate imaginary roots. Okay, even degree O degree symmetrical real roots. Okay, so that's application point of view. If you go about like control agent that determine stability range of k, root locus method verify root locations. Like in case of whenever our root locus crosses the omega axis, okay, that time we should know what's the gain. Okay, so in case of maximum gain to on the verge of count, this also called the gain margin, right? We generally find out the gain margin using the Bode plot and Nagish plot. All right, so that's a way, that's a correlation we can think here. Okay, so electrical cycle like system respond under feedback, aerospace robotics, we have to ensure the actuator stability performance. Okay, and of course like controller PID, PD, some standard controller, and also our customer controller, we can find out the gains range for which system to be stable or unstable. So let us go back to question on and solve the questions. All right, now you have better understanding how we can deal with. So first we need to find out the characteristic equation. So characteristic equation means that this is like denominator polynomial of the closed loop transfer function. All right, so let us solve out. So here let us we can assume this like complete G days. Okay. So here they given GS is 1 by S plus 1 into 1 plus S plus 2. So we can see here complete transfer function equal to GS days by, since this is negative feedback, so here will be plus. If you positive feedback, it will be negative. But in generally in most of the control system, we will use the negative feedback. And our unity feedback here there, so HS transfer function will be 1. So here K S minus 1 and 1 by S plus 1 into S plus 2. Okay. So K S minus 1 1 by S plus 1 okay na. So let us solve out what will get. S minus 1 S plus 2 okay. For example, like in this we get the this our characteristic polynomial. Okay, we generally put TS. Okay, numerator polynomial and denominator polynomial. So if all poles we know the our explicit form, easily we can find out, right? But here is a we need to find out. Let us only consider the our denominator polynomial. This is also called the custody equation polynomial. Okay, so here let us, I think some problem writing for today. So 2s 3s plus 2 plus ks minus k. Alright. So let me check once k into s minus 1. Alright. So s square plus 3s plus ks. So 3 plus k s minus plus 2 minus k. Here is minus, okay, equal to this is a we need to ensure it. Okay, so here if you talk about characteristic polynomial, so then no need to put here 0. If you talk about characteristic equation, then put here 0. Okay, so what we need to do right now, in case of our author which what we need to check first, our all coefficient signs should be same. So 3 plus k greater than 0 and 2 minus k greater than 0. So k, I think in this polynomial will be Rao which I don't think should be required. Let us see. This question very simple. Minus 3. Here k less than 2. Okay. So our k range is, you can see this is a minus 3 and this is 2. So the k range should be like that. Minus 3 greater than minus 3 Let me check back. So here our in case of stable, okay, our k range should be get less than 2. All right, so let me check, go back this answer. Okay, they given that stable for all k greater than 2, no. Unstable for all k greater than 2, yes. Unstable for all k greater than 1, no. Here you can see our range is -3 to +2. In this we can find out the stable system. Okay, so this also not, sorry, this is unstable, right? Here they are saying the unstable, but our but we solve, we get the stable. Okay, -3 to, okay, unstable for all k greater than 1. But can we say all k greater than 1? Greater than 1. Hmm. Here is a -3 to 2. If k greater than 1 but less than 2, right? Range should be managed. I think my perspective, the answer will be this, B is correct answer. Okay, you can also check out and you can post on comments, okay, if any possibility there. So that's the question. I think hope you understood. In this, I think because this is a second order, so no need to make a Routh or which is very simple. If you try to make it also, it will be get semi answer, right? Because whatever we apply this condition here, 3 by k greater than 0 alpha, sorry, this is 2 minus k greater than 0 in case of our first column of the, let us apply it what I want to convey here. So 1 and 2 minus k, this is 1 and 2 minus k. Okay, and s power 1 and s power 0. So s power 1 is here 3 plus k. Okay, so this is 0 is not correct, then if you multiply this, then multiply this is going 0, divided by 3 plus k, again you will get the 2 minus k. So we want our system is stable, right? So 1 is already known that this is positive value, but 3 plus k, this k turn 0, and 2 minus k, this k turn 0. So it means k less than -3, sorry, k greater than -3 and k less than 2. Okay, so this range should be fulfilled because here told that stable for all k greater than 1, it may be k, no, it should be less than 2 also. Okay, hope so this question you understood, well understood. So that's all, thanks for watching.